Generative AI has reached a point where the core engineering challenge has moved from architectural research to the logistics of serving models reliably at scale. A model that runs in a development notebook often fails when exposed to 10,000 concurrent users. To understand the bottleneck, we have to isolate how these models actually operate. Model pre-training is a discrete event. It involves processing terabytes of data to update billions of parameters over weeks of GPU time, aiming to minimize a specific loss function. Inference is a real-time operational pass. The parameters are fixed. The system transforms a user's input into a response through a single forward pass, operating under strict latency constraints. This process is restricted by the hardware environment. The primary constraints are the available GPU memory, VRAM, and the speed at which data can move across the memory bus. Performance in this environment is not a function of the model architecture alone. It requires an understanding of the entire execution stack, from high-level API requests down to low-level CUDA kernels and GPU memory allocators. High-performance AI is an emergent property. It is the result of the interaction between mathematical model structures, specialized serving frameworks, and physical hardware limitations. The transformer decoder is the standard architectural foundation for modern large language models. These models are autoregressive. They generate text sequentially, producing exactly one token at a time. Each new token is conditioned on the entire preceding sequence. Self-attention computes queries, keys, and values. Recomputing this for every preceding token creates massive O(n)² complexity and delay. To solve this, engineers store the constant key and value vectors in a GPU key-value cache. This simple memory lookup drops computational complexity to O(n). Like the model weights, which are static and read-only, the KV cache is a dynamic piece of state. It grows linearly with both the sequence length and the number of concurrent users. By eradicating a repetitive computational step, engineers made high-speed token generation feasible. However, this engineering trade-off creates a memory bottleneck that determines the system's total capacity. This memory constraint raises a question: why can't we simply solve the problem by using processors with higher calculation speeds? The roofline model maps GPU performance bounds. It identifies a ridge point between memory and compute limits. The initial parallel prefill phase has high arithmetic intensity, sitting on the compute-bound plateau. Conversely, generating individual tokens during the decode phase is entirely memory-bound. Here, the GPU waits for data from memory rather than performing calculations. Performance is governed by the physical memory bus, not the calculation course. This is why the leap from the NVIDIA H100 to the H200 focused on memory bandwidth over raw processing. The H200 increased data transfer to 4.8 terabytes per second. This 40% increase hauls the KV cache faster during every decode step. Because LLM token generation has low arithmetic intensity, a GPU with higher peak T-flops is often underutilized. Inference speed is chained to the physical speed of the memory bus. Historically, static memory allocation reserved maximum space up front. This contiguous allocation caused severe fragmentation, wasting up to 80% of VRAM on tokens never generated. Page detention solved this by applying virtual memory paging to the GPU, shattering the rigid block into non-contiguous chunks. The KV cache is divided into small, fixed-size blocks of 16 tokens. The system uses a logical-to-physical block table to allocate these chunks on the fly, storing data non-contiguously. This approach enables prefix caching. Multiple user requests can point to the same cached blocks for a shared system prompt, avoiding redundant computation and storage. By treating GPU memory like an operating system treats RAM, engineers eliminated internal fragmentation. This allows systems to utilize nearly 100% of available VRAM. Scheduling presents the final bottleneck. In static batching, the GPU processes requests in a group and waits for the longest response, leaving the hardware idle. Continuous batching solves this by evaluating the queue at every single decoding step. As soon as one sequence ends, it is evicted, and a new request is immediately inserted into the next forward pass. To prevent massive prompts from blocking other users, engines use chunked prefill. Large prompts are broken down and interleaved with decoding steps to smooth latency. Some techniques bypass the sequential nature of the decode phase entirely. Speculative decoding allows the system to generate multiple tokens in a single forward pass. In a draft and verify setup, a small model guesses a sequence of tokens. The massive target model then verifies all of them simultaneously in parallel. Correct guesses are accepted in one step. Advanced variants like Eagle 3 achieve 4 times the speed by extrapolating tokens from the model's own internal feature layers, removing the draft model. When physical memory bandwidth creates a speed limit, engineers use asynchronous scheduling and probabilistic guessing to reclaim wasted cycles and multiply throughput. As models grow toward 400 billion parameters, they outgrow the physical capacity of any single machine. This has led to disaggregated architecture, where prefill and decode phases are separated onto different hardware clusters. Specialized prefill nodes process incoming prompts, then stream the resulting KV cache over a high-speed network to decode nodes, optimized for high-bandwidth token generation. Industry professionals track the success of these systems using 4 metrics: time to first token, which measures prefill efficiency, and time per output token, which measures streaming speed. They also monitor model flops utilization to track compute efficiency and model bandwidth utilization to ensure the memory bus is fully optimized. The modern inference engineer is a systems architect bridging the gap between CUDA kernel optimization, memory paging, and network topography. Mastery of this hardware-software execution stack is the difference between an academic model and a viable production-grade utility.